So I'm going to talk about energetic properties of stellar pulsation across the HR diagram. And it is impossible to start this talk without this Jorgen's diagram, showing diversity of stellar pulsation. So we can meet pulsation among main sequence stars, subgiants, giants, red giants, supergiants, amongst subdwarfs, hot subdwarfs, white dwarfs, and here I put also a prediction for pulsation instability in M dwarf stars, and also some instability region for slowly pulsating B-type supergiants. Up to now, we have one star which represents this class of pulsation. Okay, so what do we mean by energetic properties? This is all what results mainly from non-adiabatic computations. That is excitation of pulsation modes and how the temperature changes during the pulsation cycle. Also kinetic energy of a mode and mode amplitude, height, and the line width. This is typical for solar-like oscillations. And in principle, we have two driving mechanisms connected with thermal processes and dynamical processes. In the case of thermal processes, we have self-excitation. That means that some layers operates like a heat engine. We have also convective blocking, that the radiative flux is perturbed at the base of convective envelope. And as for dynamical processes, we have turbulent convection, usually subphotospheric convection, like in the solar-like stars, and also tidal effects. And as for self-excitation, we have to consider work integral. This is the net energy gain by the mode during the one pulsational cycle. And we can write this in this form. Here we have the perturbation of the energy generation rate, and we have the flux, which can be radiative and also convective. And this term connected with the energy generation rate is so-called epsilon mechanism, and in the quasi-adiabatic approximation, it has this form. And because this derivative of the nuclear energy generation are always positive over temperature and density, this mechanism contribute always positive to the work integral, but usually it is negligible because of the small amplitude in the deep interior. And if we can neglect this term and also the perturbation of convective flux, this is so-called convective frozen approximation, we can write the work integral in this form, and in the diffusion approximation, the perturbation of divergency of radiative flux is like this. So where the perturbation of local luminosity can be written in this form. So here, this term is the radiative dissipation. This is a damping effect. This is a gamma effect. This is a direct influence of the temperature variation on the luminosity variation. And this is so-called R effect, termed by Baker. And what is this is a small effect which contribute positively. And here we have, this is the most important effect as for the driving of the stellar self-excitation. This is a kappa effect connected with the perturbation of the opacity. And as for this kappa, sometimes plus gamma mechanism, this mechanism is, of course, as you know, connected with these 4 bumps. This is hydrogen bump, this is helium bump, and this is Z bump, and this is deep opacity bump. Okay. And this is the evolution of eigenfrequency as a function of effective temperature. This is evolution. So we have, here we have radial modes, dipole modes, quadruple modes, and octuple modes. Dots are for unstable modes, and circles are for stable modes. So here we can see that the fundamental mode is almost, is actually unstable during the whole evolution on main sequence. For example, for non-radial modes, we can have some gravity modes, and to show the nature of this mode, here I plotted the ratio of the gravity energy to the total energy of the mode for a dipole, for several dipole and quadruple modes. This is P1, P2, G1, and G2. And so what you can see here, that at the beginning of the evolution on main sequence, G1 mode is almost pure gravity modes, and then with evolution, the character of this mode changes. And this is for L equal to mode. This is, of course, connected with the avoidant crossing phenomenon. And this is evolution of the eta parameter. This is the normalized work integral. So the value for eta is from -1 to +1, and eta greater than 0 means unstable modes. So these are typical, this is ZAMS and this is TAMS. And these are typical frequencies excited in beta Cephei stars. And on the right, you have just one model, but for different L values. So what we can see that for the higher degree modes, we can have, we have 2 instabilities, here and here. So I found in this model instability up to about L equal 30. And to compare the results for OPAL and OP data, so what is well known for OP models, that this bump at low frequencies is higher. This is connected with the fact that the opacity bump, Z opacity bump, is located at the lower temperature for this opacity data. And some examples of the work integral and the eigenfunction of pressure. So modes, generally modes in beta Cephei stars are driven by the Z opacity bump, and here we have the differential work integral, and eta is plus 0.06, so the mode is globally excited. Here we have damping below the Z opacity bump, and here we have driving, and driving overcomes damping, and the mode is globally unstable. And so what we can see here also, that the kinetic energy, this is the distribution of kinetic energy, and the ratio of the kinetic gravity energy to the total energy is just 1%. And this is gravity mode, L1G7, and this mode is stable. This is from this lower frequency, lower frequency bump. So this mode is stable, mostly due to the damping below the Z opacity bump, but also below the deep opacity bump. And here is the distribution of the kinetic density energy. And yes, and this unstable mode L equals 6 G15. This mode is unstable with the frequency 1.9, and is excited by the Z opacity bump. And this is the evolution of frequency for modes excited in models with 5 solar masses. This is L equal 1, L equal 2, L equal 3 modes. Okay. And this is the evolution of the instability parameter eta. So you can see here unstable dipole modes for opal data. So here we have typical frequencies for slowly pulsating beta stars. And here is the instability parameter for higher L values. And I found instability in this model up to L equals 17. And a comparison between opal and OP models. So here we have instability already from ZAMS. But also you can notice some local maximum at higher frequencies. And this is a typical mode excited in a model with 5 solar mass in the state of, on the main sequence. This is a work integral. The mode is excited by the Z opacity band, of course. And the L1P1 mode is damped due to the strong damping below the Z opacity bump. And this is the distribution of kinetic energy. And this is a very interesting mode, which surprised me very much because I never saw such a differential work integral for this model on the main sequence. Because what you can see here is you can see that there is some driving very deep in the star where we have where the nuclear energy is generated. So this is connected with so-called epsilon mechanism. And this mode has a very large amplitude of this pressure eigenfunction in this region. Okay, and this is for 1.8 solar masses. This is evolution of frequency along main sequence again. So this is L equals 0, 1, 2, and 3. And we can see that for these models, higher frequencies modes are excited. And here again you can see evolution of eta parameter for this model. So here you can see a typical frequencies excited in delta Scuti stars. This is again from ZAMS to TAMS. But here you have also some local maximum of eta, around 1-2 cycles per day. And for models which are more evolved, but still on main sequence, close to ZAMS, here you have some instability. And on the right, you have instability for modes from L equal 1 to L equal 7. And for this model, I found instability up to L equal 16. And this is just a comparison between opal and OP. So this local maximum of eta is lower in the case of OP models. And this is a work integral for the typical mode excited in delta Scuti star. This is a work integral. Modes are unstable because of the opacity band located, helium opacity band, and with some addition of hydrogen opacity band. And this is a kinetic energy of the mode. And the gravity mode, L equal 1 G17, is damped because of a strong damping, but this damping is below the Z opacity bump. And here we have actually addition to driving the mode. And yes, and this is this mode which I found unstable in this model. This is close to Thames. This is the mode A1G57 with the frequency 0.5. And what we can see here, that here is a strong damping, but here the mode can be driven by this local opacity bump connected with the recombination of hydrogen. So as for low frequencies in Kepler delta Scuti stars, which were recently studied by Luis Ballona, maybe this is convective flux blocking, like Luis suggested, but maybe there is some problem still with opacity, or the stars are near terminal H-band sequence. And as for delta Scuti stars, we cannot forget about the convection pulsation coupling, because sometimes convection is so effective that this frozen approximation for the convective flux is not valid. And here is an example from this paper of Marmont 1. Here we have frozen convective, and here is a time-dependent convective for L0 and L2 modes. So we can see that if we include time-dependent convection, the instability ends earlier. And the opacity seems to be a never-ending story, because now we have OPAL, OP, also Los Alamos data has been activated, and also recently Sugier published some new opacity data. This is a combination of OPAL plus CoRoT opacities. And what he, okay, so this is the kappa, this is the mean Rosaland opacity as a function of effective temperature for some model of 5, 10, and 1.8 solar mass for different opacity data. So what we can see that generally Los Alamos opacities are a little bit lower. And it has, of course, consequences that this is eta as a function of frequency for three seismic models of New Erie, calculated with 3 opacity data. So here you have, in blue you have OP, in green you have OPAL, and this is the situation for these models. But and for Los Alamos data, we can see that all modes, actually all modes except, but this one are stable. So with Los Alamos data, we have a problem with instability. And this new data, opacity data by Sugier, he found some new bump at effective logarithm of temperature equal 5.06. So maybe this new opacity bump will solve at least some of the problems. And I have to mention also here about white dwarfs, because these are very important objects. Most stars will end up as white dwarfs. This is a diagram of Gilles Fontaine showing different kind of pulsating white dwarf and also hot subdwarfs. And now we have about 6 classes of pulsating white dwarf. And here I mention only about the 3 most well-known. About W Virginis star. This is these are energetic properties for one of typical mode excited in this model. This is L equal 1 and equal 7 mode. Here you can see differential work integral and the running or cumulative work integral. So if it is plus, the mode is unstable. Here the modes are, pulsation are driven by the deep opacity bump, and in yellow you have a thin convection zone, which is the convection here is negligible. And this is for the V777 Hercules model. Here the convection is important because convective flux to the total is sometimes even 98%. So the convection plays an important role in driving this pulsation, and the mechanism is called opacity, convection opacity mechanism. This is due to the recombination of helium in the envelope. And this is the Z30 star model. This is also typical mode excited in this star, L equal 1, N equal 7. And also, in this case, the pulsations are driven by also by a convection opacity mechanism, but connected with the recombination of hydrogen in envelope. And hot subdwarfs, recent review by Susan Randall, she mentioned 6 different types. And here we have a iron profile, which results from equilibrium between gravitational settling and radiative levitation. And we have here is just an artificial enrichment of helium. And here we can see the work integral for this reference model, which has a proper profile of iron. And this is model which has an artificial enrichment of iron. Okay, so B-type supergiants. So using MESA code and non-adiabatic pulsation code, we found some instability on the blue loop because we know one star which is so-called slowly pulsating B-type supergiant, and it is located somewhere here. And the question is about its evolutionary status, whether this is in the hydrogen shell burning phase or helium core burning phase, or whether this is blue loop model or after TAMS model. And this is the helium shell burning model. This is eta versus frequency, and this is the second model. These models have comparable temperatures, comparable location on the HR diagram, and so here you can see in this model you can see the regular patterns which is connected with the mode trapping, and here we have one instability and the second instability, and in the case of this model only very low frequency mode are excited. Okay, so this is the kinetic energy. These modes are excited. This is unstable mode, this is stable mode in model 1, and again in model 2, unstable mode and stable mode. And these modes, in both cases, these modes are excited, pulsations are excited due to Z opacity band. And epsilon mechanism suggested by Ledoux in 1941. This is from paper of this man. I don't know what is the pronunciation, but what is important is this is the propagation diagram, but also showing the energy generation rate in red, and this layer where hydrogen, this is the hydrogen burning shell, and here epsilon mechanism can operate. And this is work integral for unstable mode and stable mode. But the problem is that there is no agreement between observation of, this is for oscillation spectrum of Riegel, and these are computations. So all these modes are stable. And epsilon mechanism was also suggested for population 3 stars, that some stars with such masses below 13 solar mass can have unstable G1 and G2 dipole modes. This is the growth rate as a function of evolution. this evolution of growth rate for G1 and for G1 mode. Okay, and for different masses. Okay. And instability, pulsation instability is also predicted for M dwarfs by excited by the helium-3 burning or deuterium burning, and also in some post-extremely horizontal branch white dwarfs of this type located here. Sorry. And just a few words about the effects of rotation of pulsation, because it is very important. Eta parameters depends not only on frequency and the shape of eigenfunctions, but also on frequency. In the case of P modes, usually we have to take into account the centrifugal force. In the case of slow modes, like G modes, we have to take into account Coriolis force. And this is an example from this paper. This is a cumulative work, integral for sectoral L equal 2 mode, P mode, and this is the ratio of the angular rotational frequency to the dynamical frequency. So if we have zero rotation, the mode is unstable. If we include rotation, mode is stable. And this is from a paper of Rich Townsend. This is the effect of Coriolis force on the instability domains for different values of rotational velocity. This is a period as a function of effective temperature. And here you can see instabilities for different modes. Okay, so this is for retrograde modes. This is an example of work integral for two different values of rotational velocity. So here we have stable modes, here we have unstable modes for the higher value of rotation. And solar light oscillation, there are many talks during this conference about this, so maybe I will not say too much about this. What is important are so scaling relations, which are intrinsically related to the mode properties, like the mode life width or damping rate or height. And thanks to this mission, like CoRoT and Kepler, we can find some empirical relations, like the light width versus effective temperature for red giants or for main sequence and supergiant stars. And this relation can be confronted with theory. And well, tidal effects, I think I don't have time for this. Okay, this is what is interesting that recently in paper by Silvotti et al., they found pulsation which can be tidally excited by a planetary companion, and this planet orbits as a hot subdwarf. And conclusion, so diversity of stellar pulsation allow us to study different kind of stars and different properties. And what is important that the seismic model, a good seismic model should account not only on frequency, but also about these all mode properties. And more data means better understanding, new solution, but also new challenges, new problems. But now it seems that thanks to all this space mission, we can do precision asteroseismology, which means that we can reproduce not only frequencies, but also mode properties. Okay, so thank you for your attention.
Thank you. So we have maybe time for one question, quick question, because we're a bit...
Yeah, possibly one of the biggest problems that space photometry has uncovered are the low frequencies in Daszynska-Daszkiewicz stars, as you mentioned. And you suggest that perhaps it's due to an opacity problem. I don't think this can be, because in order to fix that an opacity problem, you have to change the opacities by orders of magnitude. And although there could be some inaccuracies in the opacities, I don't believe there's an
But
order
in
of
the
magnitude
case-
change in opacity.
But in the case of beta Zeta stars, this is not one order of magnitude. We are very close already to instability in some cases.
I agree for the B stars, but now I'm talking about the Daszynska-Daszkiewicz stars, the low frequencies.
Yeah,
I don't see how that can be explained by
but for
opacity.
some low temperature models, still on main sequence, I found unstable modes which have frequencies of about 0.5.